Apart from Airframe and Powerplant Mechanics General Handbook, 9A. DC generators. Energy for the operation of most electrical equipment in an airplane depends upon the electrical energy supplied by a generator. A generator is any machine which converts mechanical energy into electrical energy by electromagnetic induction. A generator designed to produce alternating current energy is called an AC generator, or alternator. A generator which produces direct current energy is called a DC generator. Both types operate by inducing an AC voltage in coils by varying the amount and direction of the magnetic flux cutting through the coils. For airplanes equipped with direct current electrical systems, the DC generator is a regular source of electrical energy. One or more DC generators, driven by the engine, supply electrical energy for the operation of all units in the electrical system, as well as energy for charging the battery. The number of generators used is determined by the power requirement of a particular airplane. In most cases, only one generator is driven by each engine, but in some large airplanes, two generators are driven by a single engine. Aircraft equipped with alternating current systems use electrical energy supplied by AC generators, also called alternators. Theory of operation. Conductor. The conductor and the magnetic field make up an elementary generator. This simple generator is illustrated in Figure 9:1, together with the components of an external generator circuit which collect and use the energy produced by the simple generator. The loop of wire A and B of Figure 9:1 is arranged to rotate in a magnetic field. When the plane of the loop of wire is parallel to the magnetic lines of force, the voltage induced in the loop causes a current to flow in the direction indicated by the arrows in Figure 9:1. The voltage induced at this position is maximum, since the wires are cutting the lines of force at right angles and are thus cutting more lines of force per second than in any other position relative to the magnetic field. As the loop approaches the vertical position shown in Figure 9:2, the induced voltage decreases because both sides of the loop A and B are approximately parallel to the lines of force and in the study of alternating current. Basic generator principles were introduced to explain the generation of an AC voltage by a coil rotating in a magnetic field. Since this is the basis for all generator operation, it is necessary to review the principles of generation of electrical energy. When lines of magnetic force are cut by a conductor passing through them, voltage is induced in the conductor. The strength of the induced voltage is dependent upon the speed of the conductor and the strength of the magnetic field. If the ends of the conductor are connected to form a complete circuit, the current is induced in the Figure 9:1, inducing maximum voltage in an elementary generator. Figure 9:2, inducing minimum voltage in an elementary generator. Figure 9:4, inducing a minimum voltage in the opposite direction. The rate of cutting is reduced. When the loop is vertical, no lines of force are cut since the wires are momentarily traveling parallel to the magnetic lines of force, and there is no induced voltage. As the rotation of the loop continues, the number of lines of force cut increases until the loop has rotated the end additional 90 to a horizontal plane. As shown in Figure 9:3, the number of lines of force cut and the induced voltage once again are maximum. The direction of cutting, however, is in the opposite direction to that occurring in Figures 9:1 and 9:2. So the direction polarity of the induced voltage is reversed. As rotation of the loop continues, the number of lines of force having been cut again decreases, and the induced voltage becomes zero at the position shown in Figure 9:4, since the wires A and B are again parallel to the magnetic lines of force. If the voltage induced throughout the entire 360 of rotation is plotted, the curve shown in Figure 9.25 results. This voltage is called an alternating voltage because of its reversal from positive to negative values first in one direction and then in the other. To use the voltage generated in the loop for producing a current flow in an external circuit, some means must be provided to connect the loop of wire in series with the external circuit. Such an electrical connection can be effected by opening the loop of wire and connecting its two ends to two metal rings, called slip rings, against which two metal or carbon brushes ride. The brushes are connected to the external circuit. By replacing the slip rings of the basic AC generator with two half cylinders, called a commutator, the basic DC generator Figure 9.6 is obtained. In this illustration, the black side of the coil is connected to the black segment and the white side of the coil to the white segment. The segments are insulated from each other. The two stationary brushes are placed on opposite sides of the commutator and are so mounted that each brush contacts each segment of the commutator as the latter revolves simultaneously with the loop. The rotating parts of a DC generator coil and commutator are called an armature. The generation of an EMF by the loop rotating in the magnetic field is the same for both AC and DC generators, but the action of the commutator produces a DC voltage. This generation of a DC voltage is described as follows for the various Figure 9.3. Inducing maximum voltage in the opposite direction. By maximum Figure 9.25. 388 output of an elementary generator. Figure I basic DC generator. H positions of the loop rotating in a magnetic field, with reference to Figure 9.7. The loop in position B of Figure 9.7 is rotating clockwise, but no lines of force are cut by the coil sides and no EMF is generated. The black brush is shown coming into contact with the black segment of the commutator, and the white brush is just coming into contact with the white segment. In position B of Figure 9.7, the flux is being cut at a maximum rate and the induced EMF is maximum. At this time, the black brush is contacting the black segment and the white brush is contacting the white segment. The deflection of the meter is toward the right, indicating the polarity of the output voltage. At position C of Figure 9.7, the loop has completed 180 of rotation. Again, no flux lines are being cut and the output voltage is 0. The important condition to observe at position C is the action of the segments and brushes. The black brush at the 180 angle is contacting both black and white segments on one side of the commutator, and the white brush is contacting both segments on the other side of the commutator. After the loop rotates slightly past the 180 point, the black brush is contacting only the white segment and the white brush is contacting only the black segment. Because of this switching of commutator elements, the black brush is always in contact with the coil side moving downward, and the white brush is always in contact with the coil side moving upward. Though the current actually reverses its direction in the loop in exactly the same way as in the AC generator, commutator action causes the current to flow always in the same direction through the external circuit or meter. The graph of one cycle of operation is shown in Figure 9.7. The generation of EMF for positions A, B, and C is the same as for the basic AC generator, but at position D, commutator L Figure 9.7. L revolution for operation of a basic DC generator. Action reverses the current in the external circuit, and the second half cycle has the same waveform as the first half cycle. The process of commutation is sometimes called rectification, since rectification is the converting of an AC voltage to a dot voltage. At the instant that each brush is contacting two segments on the commutator positions A, C, and E in figure 9 to 7, the direct short circuit is produced. If an EMF were generated in the loop T this time, a high current would flow in the circuit, causing an arc and thus damaging the commutator. For this reason, the brushes must be placed in the exact position where the short will occur when the generated EMF is zero. This position is called the neutral plane. The voltage generated by the basic DC generator in figure %7 varies from 0 to its maximum value twice for each revolution of the loop. This variation of DC voltage is called ripple, and may be reduced by using more loops, or coils, as shown in the figure 9 to 8. As the number of loops is increased, the variation between maximum and minimum values of voltage is reduced via figure 9 to 8, and the output voltage of the generator approaches the steady DC value. In the figure 9 to 8, the number of commutator segments is increased in direct proportion to the number of loops. That is, there are 2 segments for 1 loop, 4 segments for 2 loops, and 8 segments for 4 loops. The voltage induced in a single turn loop is small. Increasing the number of loops does not increase the maximum value of generated voltage, but increasing the number of turns in each loop will increase this value. Within narrow limits, the output voltage of a DC generator is determined by the product of the number of turns per loop, the total flux per pair of poles in the machine, and the speed of rotation of the armature. An AC generator, or alternator, and a DC generator are identical as far as the method of generating voltage in the rotating loop is concerned. However, if the current IE taken from the loop by slip rings, it is an alternating current, and the generator is called an AC generator, or alternator. If the current is collected by a commutator, it is direct current, and the generator is called a DC generator. Construction features of DC generators. Generators used on aircraft may differ somewhat in design, since they are made by various manufacturers. All, however, are of the same general construction and operate similarly. The major parts, or assemblies, of a DC generator are a field frame or yoke, a rotating armature, and a brush assembly. The parts of a typical aircraft generator are shown in figure F9. Field frame 0 IW revolutions. I1 figure 9 to 8. Increasing the number of coils reduces the ripple in the voltage. The field frame is also called yoke, which is the foundation or frame for the generator. The frame has 2 functions. It completes the magnetic circuit between the poles and acts as a mechanical support for the other parts of the generator. In the figure 9 to 10, the frame for a 2-pole generator is shown in a cross-sectional view. A 4-pole generator frame is shown in the figure 9 to 10. In small generators, the frame is made of one piece of iron, but in larger generators, it is usually made up of 2 parts bolted together. The frame has high magnetic properties and, together with the pole pieces, forms the major part of the magnetic circuit. The field OLEF shown in figure %low are bolted to the inside of the frame and form the core on which the field coil windings are mounted. The poles are usually laminated to reduce eddy current and figure 9 to 9. Typical %volt aircraft generator. Current losses and serve the same purpose as the iron core of an electromagnet, that is, they concentrate the lines of force produced by the field coils. The entire frame, including field poles, is made from high-quality magnetic iron or sheet steel. A practical DC generator uses electromagnets instead of permanent magnets. To produce a magnetic field of the necessary strength with permanent magnets would greatly increase the physical size of the generator. The field coils are made up of many turns of insulated wire and are usually wound on a form which fits over the iron core of the pole to which it is securely fastened. Figure 911. The exciting current, which is used to produce the magnetic field and which flows through the field coils, is obtained from an external source or from the generated DC of the machine. No electrical connection exists between the windings of the field coils and the pole pieces. Most field coils are connected in such a manner that the poles show alternate polarity. Since there is always one north pole for each south pole, there must always be an even number of poles in any generator. Note that the pole pieces in Figure 9 to 10 project from the frame. Because there offers a great amount of reluctance to the magnetic field, this design reduces the length of the air gap between the poles and the rotating armature and increases the efficiency of the generator. When the pole pieces are made to project as shown in Figure 9 to 10, they are called salon poles. Armature. The armature assembly consists of armature coils wound on an iron core, a commutator, and associated mechanical parts. Mounted on a shaft, it rotates through the magnetic field produced by the field coils. The core of the armature acts as an iron conductor in the magnetic field and, for this reason, is laminated to prevent the circulation of eddy currents. There are two general kinds of armatures, the ring and the drum. Figure 9 to 12 shows a ring-type armature made up of an iron core, an egg-section winding, and an 8-segment commutator. This kind of armature is rarely used. Most generators use the drum-type armature. The drum-type armature Figure 9 to 13 has coils placed in slots in the core, but there is no electrical connection between the coils and core. The use of slots increases the mechanical safety of the armature. Usually, the coils are held in place in the slots by means of wooden or fiber wedges. The connections of the individual coils, called coil ends, are brought out to individual segments on the commutator. Figure 9 to 11. A field coil removed from a field pole. Flanges fitted with bolts. Rings of mica insulate the segments from the flanges. The raised portion of each segment is called a riser, and the leads from the armature coils are soldered to the risers. When the segments have no risers, the leads are soldered to short slits in the ends of the segments. The brushes ride on the surface of the commutator, forming the electrical contact between the armature coils and the external circuit. A flexible, braided copper conductor, common one white called a pigtail, connects each brush to the external circuit. The brushes, usually made of high-grade carbon and held in place by brush holders insulated from the frame, are free to slide up and down in their holders in order to follow any irregularities in the surface of the commutator. The brushes are usually adjustable so that the pressure of the brushes on the commutator can be varied and the position of the brushes with respect to the segments can be adjusted. The constant making and breaking of connections to the coils in which a voltage is being Figure 9 to 10. The 2-pole and a 4-PDE frame assembly. Commutators Figure 9 to 14 shows a cross-sectional view of a typical commutator. The commutator is located at the end of an armature and consists of wedge-shaped segments of hard-drawn copper, insulated from each other by thin sheets of mica. The segments are held in place by steel V-rings or clamp. Figure 9 to 12. An 8-section, ring-type armature. Commutator slots coils Figure 9 to 13. The drum-type armature. Enough to provide reasonable brush life. Since the contact resistance of carbon is fairly high, the brush must be quite large to provide a large area of contact. The commutator surface highly polished to reduce friction as much as possible. Oil or grease must never be used on a commutator, and extreme care must be used when cleaning it to avoid marring or scratching the surface. Tightening nut induced necessitates the use of material for brushes which has a definite contact resistance. Also, this material must be such that the friction between the commutator and the brush is low, to prevent excessive wear. For these reasons, the material commonly used for brushes is high-grade carbon. The carbon must be soft enough to prevent undue wear of the commutator and yet hard our outer rings for insulation. Figure %14. Commutator with portion removed to show construction. 393 types of DC generators. There are 3 types of DC generators: series wound, shunt wound, and shunt series or compound wound. The difference in type depends on the relationship of the field winding to the external circuit. Series wound DC generators. Generators in airplanes have field windings which are connected either in shunt or in compound. Shunt wound DC generators. The field winding of a series generator is connected in series with the external circuit, called the load. Figure 9-15. The field coils are composed of a few turns of large wire. The magnetic field strength depends more on the current flow rather than the number of turns in the coil. Series generators have very poor voltage regulation under changing load, since the greater the current through the field coils to the external circuit, the greater the induced EMF and the greater the terminal or output voltage. Therefore, when the load is increased, the voltage increases. Likewise, when the load is decreased, the voltage decreases. The output voltage of a series wound generator may be controlled by a rheostat in parallel with the field windings, as shown in the above figure 9-15. Since the series wound generator has such poor regulation, it is never employed as an airplane load plus figure %15. To load diagram and schematic of a series wound generator. A generator having a field winding connected in parallel with the external circuit is called a shunt generator, as shown in A and B figure %16. The field coils of a shunt generator contain many turns of small wire. The magnetic strength is derived from a large number of turns rather than the current strength through the coils. If a constant voltage is desired, the shunt wound generator is not suitable for rapidly fluctuating loads. Any increase in load causes a decrease in the terminal or output voltage, and any decrease in load causes an increase in terminal voltage. Since the armature and the load are connected in series, all current flowing in the external circuit passes through the armature winding. Because of the resistance in the armature winding, there is a voltage drop. CR drop equals current X resistance. As the load increases, the armature current increases and the IR drop in the armature increases. The voltage delivered to the terminals is the difference between the induced voltage and the voltage drop. Therefore, there is a decrease in terminal voltage. This decrease in voltage causes a decrease in field strength, because the current in the field coils decreases in proportion to the decrease in terminal voltage. With a weaker field, the voltage is further decreased. When the load decreases, the output voltage increases accordingly, and a larger current flows in the windings. This action is cumulative, so the output voltage continues to rise to a point called field saturation, after which there is no further increase in output voltage. The terminal voltage of a shunt generator can be controlled by means of a rheostat inserted in series with the field windings as shown in figure 9-16. As the resistance is increased, the field current is reduced. Consequently, the generated voltage is reduced also. For a given setting of the field rheostat, the terminal voltage at the armature brushes will be approximately equal to the generated voltage minus the IR drop produced by the load current in the armature. Thus, the voltage at the terminals of the generator will drop as the load is applied. Certain voltage-sensitive devices are available which automatically adjust the field rheostat to compensate for variations in arm 0 to low shunt CL-it plane circuit. 0 Figure 9 to 16. Shunt wound generator influences the main field flux of the generator. The diagrammatic and a schematic illustration of a compound wound generator is shown in A and B of Figure 9 to 17. If the ampere turns of the series field act in the same direction as those of the shunt field, the combined magnetomotive force is equal to the sum of the series and shunt field components. Load is added to a compound generator in the same manner in which load is added to a shunt generator, by increasing the number of parallel paths across the generator terminals. Thus, the decrease in total load resistance with added load is accompanied by an increase in armature circuit and series field circuit current. Load. When these devices are used, the terminal voltage remains essentially constant. Compound wound DC generators. A compound wound generator combines a series winding and a shunt winding in such a way that the characteristics of each are used to advantage. The series field coils are made of a relatively small number of turns of large copper conductor, either circular or rectangular in cross-section, and are connected in series with the armature circuit. These coils are mounted on the same poles on which the shunt field coils are mounted and, therefore, contribute a magnetomotive force which series field coil shunt field coil load negative for the TT9 compound wound. Figure 9 to 17. Compound wound generator 395. The effect of the additive series field is that of increased field flux with increased load. The extent of the increased field flux depends on the degree of saturation of the field as determined by the shunt field current. Thus, the terminal voltage of the generator may increase or decrease with load, depending on the influence of the series field coils. This influence is referred to as the degree of compounding. A flat compound generator is one in which the no-load and full-load voltages have the same value, whereas an undercompound generator has a full-load voltage less than the no-load value, and an overcompound generator has a full-load voltage which is higher than the no-load value. Changes in terminal voltage with increasing load depends upon the degree of compounding. If the series field aids the shunt field, the generator is said to be cumulative compounded. Be a figure J17. If the series field opposes the shunt field, the machine is said to be differentially compounded, or is called a differential generator. Compound generators are usually designed to be overcompounded. This feature permits varied degrees of compounding by connecting the variable shunt across the series field. Such a shunt is sometimes called a diverter. Compound generators are used where voltage regulation is of prime importance. Differential generators have somewhat the same characteristics as series generators in that they are essentially constant current generators. However, they generate rated voltage at no load, the voltage dropping materially as the load current. Figure 9 to 19. 3-wire generator increases. Constant current generators are ideally suited as power sources for electric arc welders and are used almost universally in electric arc welding. If the shunt field of a compound generator is connected across both the armature and the series field, it is known as a long shunt connection, but if the shunt field is connected across the armature alone, it is called a short shunt connection. These connections produce essentially the same generator characteristics. A summary of the characteristics of the various types of generators discussed is shown graphically in Figure 9 to 18. 3-wire mounter SP&L output current or low 100%. Figure 9 to 18. Generator characteristics. Some DC generators, called 3-wire generators, are designed to deliver 240 volts, or 120 volts from either side of a neutral wire, figure 9 to 19. This is accomplished by connecting the reactance coil to opposite sides of the commutator, with the neutral connected to the midpoint of the reactance coil. Such a reactance coil acts as a low-loss voltage divider. If resistors were used, the IR loss would be prohibitive unless the two loads were perfectly matched. The coil is built into some generators as part of the armature, with the midpoint connected to a single slip ring which the neutral contacts by means of a brush. In other generators, the two connections to the commutator are connected, in turn, to two slip rings, and the reactor is located outside the generator. In either case, the load unbalance on either side of the neutral must not be more than 25% of the rated current output of the generator. The 3-wire generator permits simultaneous operation of 120-volt lighting circuits and 240-volt motors from the same generator. Armature reaction current flowing through the armature sets of electromagnetic fields in the windings. These new fields tend to distort or bend the magnetic flux between the poles of the generator from a straight line path. Since armature current increases with load, the distortion becomes greater with an increase in load. This distortion of the magnetic $6 neutral plane via field excited, armature unexcited, and the armature excited. Field unexcited, see both field and armature excited, figure 9 to 20. Armature reaction. Field is called armature reaction and is illustrated in figure 9 to 20. Armature windings of a generator are spaced in such a way that, during rotation of the armature, there are certain positions when the brushes contact to adjacent segments, thereby shorting the armature windings to these segments. Usually, when the magnetic field is not distorted, there is no voltage being induced in the shorted windings, and, therefore, no harmful results occur from the shorting of the windings. However, when the field is distorted, a voltage is induced in these shorted windings and sparking takes place between the brushes and the commutator segments. Consequently, the commutator becomes pitted, the wear on the brushes becomes excessive, and the output of the generator is reduced. To correct this condition, the brushes are set so that the plane of the coils which are shorted by the brushes is perpendicular to the distorted magnetic field, which is accomplished by moving the brushes forward in the direction of rotation. This operation is called shifting the brushes to the neutral plane, or plane of commutation. The neutral plane is the position where the plane of the two opposite coils is perpendicular to the magnetic field in the generator. On a few generators, the brushes can be shifted manually ahead of the normal neutral plane to the neutral plane caused by field distortion. On non-adjustable brush generators, the manufacturer sets the brushes for minimum sparking. Interpoles may be used to counteract some of the effects of field distortion, since shifting the brushes is inconvenient and unsatisfactory, especially when the speed and load of the generator are changing constantly. An interpole is a pole placed between the main poles of a generator. For example, a 4-pole generator has 4 interpoles, which are north and south poles, alternately, as are the main poles. A 4-pole generator with interpoles is shown in figure 9 to 21. An interpole has the same polarity as the next main pole in the direction of rotation. The magnetic flux produced by an interpole causes the current in the armature to change direction as an armature winding passes under it. This cancels the electromagnetic fields about the armature windings. The magnetic strength of the interpoles varies with the load on the generator, and since field distortion varies with the load, The magnetic field of the interpoles counteracts the effects of the field set up around the armature windings. Generator terminals figure 9 to 21. Generator with interpoles. On most large 24-volt generators, electrical connections are made TO terminals marked B, A, and EC figure 9 to 22. The positive armature lead in the generator connects TO the B terminal. The negative armature lead connects to the E terminal. The positive end of the shunt field winding connects to terminal A, and the opposite end connects to the negative terminal brush. Terminal receives current from the negative generator brush through the shunt field winding. This current passes through the voltage regulator and back to the armature through the positive brush. Load current, which leaves the armature through the negative brushes, comes out of the E lead and passes through the load before returning to the armature through the positive brushes. Regulation of generator voltage and minimizes field distortion. Thus, the interpole tends to keep the neutral plane in the same position for all loads on the generator. Therefore, field distortion is reduced by the interpoles, and the efficiency, output, and service life of the brushes are improved. Generator ratings. The generator is rated in power output. Since a generator is designed to operate at a specified voltage, the rating usually is given as the number of amperes the generator can safely supply at its rated voltage. Generator rating and performance data are stamped on the nameplate attached to the generator. When replacing a generator, it is important to choose one of the proper rating. The rotation of generators is termed either clockwise or counterclockwise, as viewed from the driven end. Usually, the direction of rotation is stamped on the data plate. If no direction is stamped on the plate, the rotation may be marked by an arrow on the cover plate of the brush housing. It is important that a generator with the correct direction of rotation be used, otherwise the voltage will be reversed. The speed of an aircraft engine varies from idle RPM to takeoff RPM. However, during the major portion of a flight, it is a constant cruising speed. The generator drive is usually geared to revolve the generator between 1% and 1% times the engine crankshaft speed. Most aircraft generators have a speed at which they begin to produce their normal voltage. Termed the coming-in speed, it is usually about 1,500 rpm. Efficient operation of electrical equipment in an airplane depends on a constant voltage supply from the generator. Among the factors which determine the voltage output of a generator, only one, the strength of the field current, can be conveniently controlled. To illustrate this control, refer to the diagram in Figure 9 to 22, showing a simple generator with a rheostat in the field circuit. If the rheostat is set to increase the resistance in the field circuit, less current flows through the field winding and the strength of the magnetic field in which the armature rotates decreases. Consequently, the voltage output of the generator decreases. If the resistance in the field plus Figure 9 to 22. Current flow regulation of generator voltage by field rheostat. AIR systems require a different type of regulator, such as the carbon pile voltage regulator. Carbon pile voltage regulator. Thank you.